Hi everyone. It's a great pleasure to attend this conference and to introduce our recent study on dynamic facade. The title of the paper to be presented is Analysis on the Influence of Environmental Factors on Building Energy Consumption of Dynamic Facade. And I'd like to share this with you together with my co-author. We are all come from School of Architecture and Civil Engineering, Xiamen University, China. Well, dynamic facade is different from traditional building facade. It can change according to time, temperature, light, and other environmental factors, so as to improve the indoor physical environment and save energy. Therefore, in recent years, great progress has been made in the field of dynamic facade that can adapt to ambient environmental conditions. However, current studies are mostly about the morphological changes of the dynamic facade. So, this paper extends the study to 4 environmental adjustment factors, including regulation of solar radiation, adjustment of ventilation, thermal storage capacity, and thermal resistance, to explore the advantages of dynamic facade in energy saving from the perspective of energy consumption. So, why these 4 factors? First of all, solar radiation affects the heat gain of the building, thereby affecting the indoor temperature and having a greater impact on indoor comfort. And as a passive energy saving strategy, natural ventilation improves indoor thermal comfort while taking away indoor heat. Thirdly, materials with good thermal storage capacity reduces indoor temperature fluctuations caused by changes in external temperature, which minimizes the downtime of air conditioning. Finally, by controlling the thermal resistance of the skin, the heat transfer capacity of it will vary with the external environment, which also reduces the time of using the air conditioner. In a nutshell, we can improve indoor comfort by controlling these 4 factors. Okay, next, we set up a building model for simulation. The model used in this study is a single-story office building with double-glazed windows located in Xiamen, China, and it only opens the window on the south. We set the occupancy schedule according to standard for green performance calculation of civil buildings. And the evaluation indicators are building total energy consumption and energy saving. By the way, we also use the ratio of comfort time as an auxiliary index. And you can see the figure on the right and the table on the next page show the detailed dimensions and parameters of the office. Then, the performance simulation platforms, Ladybug tools, and Design Builder were used. According to the perspective performance advantages of the two software, the adjustment of solar radiation and ventilation was simulated by Ladybug and Honeybee, and the thermal storage capacity and variable thermal resistance were simulated by Design Builder. In addition, we have also established relevant simulation settings. For Group A, we added ventilation blinds on the outer glass layer and the dynamic facade to adjust solar radiation. Its variability is that the opening and opening angles of the blinds change with solar radiation and outdoor temperature. Therefore, these three factors were simulated as variables. At the same time, the model without Venetian blinds was used as a control group. For Group B, we had the amount of ventilation adjusted. Windows, a component of the building scheme, respond to the wind environment by controlling the opening ratio. So, according to the comfortable temperature range obtained by adaptive thermal comfort model, the cooling set point schedule and heating set point schedule were formed and the natural ventilation time was controlled by opening the window. We used the window ratio as a variable to increase the period of time for natural indoor ventilation as much as possible, and perform air conditioning, cooling, or heating at unsatisfactory time.
In Group C, with the k-value equal to the reference one of the walls of the test room was ended with phase-change materials. On top of that, we put up two movable sheets on the test wall, whose size and location are shown in this picture. The shading blinds open from 10 a.m. to 4 p.m. in summer to control the absorption of solar radiation. And we want to know the effect of different factors on energy saving, so here are 5 experimental groups. C1 contains 3 wall configurations with different locations of PCM layer and a reference one without PCM. C2 and C3 were set to gain insight into the influence of the melting temperature and the thickness of PCM. And in C4, we studied the difference of the energy saving rate in 4 orientations. At last, we investigated the effect of the movable sheets on the PCM enhanced wall. In the following study of thermal resistance control, we used the data from other relative papers to make sure the results are valid. As we all know, higher thermal resistance makes it more reliable to have less energy consumption. So all the test groups have the same maximum thermal resistance but different minimal thermal resistance. And all the cases were said to have high thermal resistance when the ambient temperature is above 12.5 Celsius degree and under 18 Celsius degree. Otherwise, they have low thermal resistance. Then we selected the data of one case to modify its maximum or minimum thermal resistance by gradient respectively to know which way affects more. And here are our results of numerical simulation. In Group A, it can be seen that energy saving reaches its minimum and the ratio of countable time is maximized when the blind open in negative 30 degrees with the ambient temperature at 18 Celsius degree. And in picture, when the solar radiation intensity is at 18 watts per square meter, the energy saving rate is lowest. In case B, when the ratio of opening window is 0.2, the rate of energy saving is the highest, with an acceptable proportion of countable time. And these simulation results of C group indicate that the optimal location of PCM layer is outside the insulation layer. And the right figure shows that the most energy-saving melting temperature is 12.7 Celsius degrees. As left picture shown, energy consumption decreases with increased thickness of PCM layer, but its increase of energy saving reaches the climax when the thickness changes to 30 millimeters from 20 millimeters. The right finger reveals the diverse rates of energy saving in different orientations, and it's obviously efficient to end PCM to the south wall. Then, if we look at this picture, we can see the cooperation with the dynamic shades works well, and it further reduces energy consumption. And let's turn to the group D. From our results of the simulation, the variation of thermal resistance indeed decreases energy consumption. And in most cases, it saves both cooling and heating energy consumption. Furthermore, it saves more energy to increase the max thermal resistance rather than decreases the minimum thermal resistance. So it's better to improve the façade's max thermal resistance. At the end of the simulation, we compared the energy saving rates of all above. It turned out that the four environmental factors can reduce building energy consumption. And all the rates of energy saving are shown on this page. And you can see the highest one achieved by adjusting the natural ventilation, while the adaptable insulation envelope saves the least. So we can conclude that in Xiamen, it will be more energy efficient to select a building envelope which regulates natural ventilation or combines adaptable shades with force change material. Though the adaptable insulation envelope tested make little effect on energy saving, it's still in the preliminary stage of development and may achieve better energy saving effect through continuous improvement in the future. Last but not least, the simulation analysis in this paper is all based on single factors, and the energy saving effect under the combination of multiple factors needs further studies. If you have any questions or if you are interested in our study on dynamic facade, welcome to contact us. and our email is at the bottom of the page. Thank you for your listening.